Everything that we have looked at concerning strong and weak acids also applies to strong and weak bases. So let's start with looking at weak bases. Ammonia, NH3, is an example of a weak base, which means that it doesn't react fully with water. So in order to be able to find the pH of a weak base, we need to know how many hydroxide ions we have in solution, and in order to do that, we need to know where the position of equilibrium in this reaction lies. So let's write the expression just for general equilibrium, Kc. Once again, it's concentration of products over reactants. So if I'm doing this properly, I should make sure that I have state symbols. Square brackets denote concentration, hydroxide ion, over my reactants, which is the undissociated ammonia, or the unreacted rather, ammonia, and water. Now, once again, because we're working in solution, we can assume that the concentration of water is effectively constant. So if I rearrange this expression so that both constants are on the left-hand side, so Kc times concentration of water is equal to the ammonium ion, hydroxide ion, squeeze in my AQ, divided by the concentration of ammonia. If you've been following through this series of tutorials in order, you will know that where I have one constant multiplied by another constant, I get to make up a third. And we're going to call this Kb, which is called the basicity. That is not easy to say. Basicity constant, or the base dissociation constant. So Kb, just like with Ka for a weak acid, NH4 plus, now bases are covered very lightly at A level, so this is as much about making your understanding complete as it is about producing usable expressions, but hopefully you can see how that relates to the expressions we derived for a weak acid. And for ammonia, Kb equals 1.8 times 10 to the minus 5 mole per decimeter cubed. Again, it's a small number. What does that tell us? It tells us the position of equilibrium for this reaction here lies very strongly to the left. Not many ammonia molecules react with water to form hydroxide ions and ammonium ions. And again, the use of the word reaction is probably more accurate than that of dissociation in terms of bases. How would I use this to find the pH? Because pH, as we know, is minus the log of the hydrogen ion concentration, but I don't have a hydrogen ion concentration here. Okay, so a few tutorials back, we looked at the ionic product of water. Kw, the degree to which water self-ionizes, and we saw that that expression could be written as so. So Kw equals concentration of hydrogen ions multiplied by the concentration of hydroxide ions, and at 298 K we saw that was 1.00 times 10 to the minus 14 mole squared dm to the minus 6. So finding the pH of a base, whether it's a strong base or a weak base, requires a couple of extra steps. We first have to find the hydroxide ion concentration, and then we can use this expression here to find the hydrogen ion concentration, and from there we can find the pH. So let's start by looking at the situation for a strong base. So a strong base, a good example is good old sodium hydroxide. And because it is a strong base, we can assume that it dissociates fully in solution to form sodium ions and hydroxide ions. Because we're assuming full dissociation, then we can assume that the concentration of hydroxide ions is the same as the initial concentration of the sodium hydroxide. We can see this from the equation here. It's a 1-to-1 molar ratio. So let's we want to find the pH of sodium hydroxide, and it's got a concentration of 0.1 mole per decimeter cubed. Well, ionic product of water, Kw, is equal to the hydrogen ion concentration times the hydroxide ion concentration. In this case, because we are dealing with an alkali, I know that and let's go back to my normal method, the concentration of the hydroxide ion is 0.1 mole per decimeter cubed, because we've just seen that we've got full dissociation and this is a 1-to-1 ratio. I know my value for Kw, and this would be always on your data sheet if it's not given in the actual question. If they're being nice to you, they give it in the question, which is a clue to the way to work through these calculations. If they're not, you need to remember to look for your data sheet. So that tells me that 1.00 times 10 to the minus 14 is equal to the hydrogen ion concentration multiplied by concentration of the hydroxide ions, 0.1. If I were to rearrange that, hydrogen ion concentration equals 1 times 10 to the minus 14 divided by 0.1, which equals times 10 to the minus 13. We're expecting it to be an incredibly low number. Remember, we're dealing with alkalis here. And pH equals minus the log of the hydrogen ion concentration. When you plug that into your calculator, it comes out as 13, which is what we'd expect for a very strong alkali. With the case of weak bases, we need to find the hydroxide concentration, and because they don't fully react or dissociate, we cannot assume that the original concentration of the base is the same as that of the hydroxide ions. So we've got a couple more steps. This is exactly the same as finding the pH for a weak acid to begin with. So our basic expression, we have got ammonia reacting with water to form ammonium ions in solution and hydroxide ions in solution. We know that our basicity constant Kb is equal to products over reactants, so NH4 plus OH minus over NH3. We're going to work on exactly the same assumptions as we did for a weak acid. So first of all, we know what Kb is. It is 1.8 times 10 to the minus 5 mole per decimeter cubed. We can assume, because this Kb number is so small, that to all intents and purposes the concentration of ammonia at equilibrium is unchanged. So that remains at 0.2 mole per decimeter cubed. And we can see from our equation that when ammonia reacts with water, it produces ammonium ions and hydroxide ions on a 1-to-1 basis. So we can also see there that the concentration of ammonium ions is equal to the concentration of hydroxide ions. So moving on, I can see that Kb is going to equal the hydroxide ion concentration squared over the ammonia concentration, which means that the hydroxide ion concentration squared is equal to Kb multiplied by the concentration of ammonia. Let's put some numbers into that. Let's move up. So the hydroxide ion concentration squared is equal to 1.8 times 10 to the minus 5 multiplied by 0.2, and that comes out at 3.6 times 10 to the minus 6. The hydroxide ion concentration is going to be the square root of 3.6 times 10 to the minus 6, and that comes out to be 0.00188 mole per decimeter cubed. There are not many hydroxide ions in the solution, which is what we would expect for a weak base. So I know that Kw equals H plus OH minus. So that's 1.00 times 10 to the minus 14 equals the hydrogen ion concentration multiplied by 0.00188. That gives me, when I rearrange it, a hydrogen ion concentration of 5.32 times 10 to the minus 10 to the minus 12. And pH equals minus the log of the hydrogen ion concentration. So when you plug that into your calculator, it comes out at 11.3, which is what we would expect for a fairly strong concentration of a weak base. If this has been useful, hit the subscribe button, the effortless way to support your studies. And by clicking the link in the description below, it'll take you straight to Crunch Chemistry School, where you can access my free math skills course, complete tuition, and worksheets designed specifically to build your confidence and stretch you. Together we can do this.